Hello everyone, welcome back to this session on fine tuning. In the part 1 of teaching AI to learn, we learned about the model pre-training. So what is pre-training is all about, what goes in pre-training, and we have seen Llama 3.1 8 billion parameter model. We loaded the pre-trained model into Colab Notebook and we have seen how the response looks like. In this session, we are going to focus on fine tuning. So this fine tuning is also called supervised fine tuning or instruction based fine tuning. So what we do in what is a fine tuning is all about. We take a pre-trained model and we make the model expert in a specific domain. It could be finance, it could be medical, it could be mathematics, it could be science. We make the LLM is expert in specific domain, or it could be a task-based expertise like generating a code, or maybe a customer support or medical advice. It could be anything. So that's what the fine tuning is all about. So in this session, I already made a video on what the fine tuning basics, like what is a fine tuning is all about, when to use fine tuning, like when to use RAG, when to use prompting, what is the difference between all the three. So I made a video on that. So you can watch that video to get basics of the LLM fine tuning. In this series, we are going to go in depth of the PEFT and LoRA, a technique used to fine tune LLM. And we are also going to understand like what are the different frameworks available in the to fine tune LLM. And then we are going to actually take a framework called Unsloth and then fine tune the Llama 3.1 8 billion parameter model using that particular framework on a finance data set. And then we are going to build a Gradio UI where we compare the model response before fine tuning and after fine tuning. We'll also have a DeepSeek LLM as a judge functionality where we give the response from both the models to DeepSeek LLM and ask it to evaluate the response from both the models. So that is what is going to be the focus of this session. And then with that, let's get started. So now let's understand what the LLM fine tuning is all about. In this session, I'm going to focus mostly on the LoRA technique. We'll try to get into understand the LoRA in very intuitive and in a at the same time understanding the math and bit of the technology behind it. So let's first talk about PEFT, parameter efficient fine tuning. So using a simple analogy to start with. So imagine you are having a huge robot here, which is nothing but a massive pre-trained LLM. It already knows a lot, but it is frozen. We don't want to retrain the entire thing every time we need a new skill. Like every time you want a skill on finance, I don't go to and pre-train the model again one more time. It is so expensive. You have seen to read it has got some billions of parameters. It requires a cluster of GPUs. A massive training amount time is required. It is a huge investment altogether. So instead, we used PEFT, okay, which is nothing but parameter efficient fine tuning. This is like giving the robot plug and play skill modules. Now we can plug a new skill labeled say finance into this robot. Okay, now the model provide a financial advice, plug that model. Now we want a customer support or medical QA, just insert that tiny fine-tune adapter for that use case. So the robot stays frozen. We are only updating a small efficient pieces the specific to the task. That's what makes PEFT powerful. It is faster to train, it is cheaper to deploy, and doesn't forget the old skills. So what is PEFT? This is only analogy, but we are going to see the technical details in the coming slide. But to understand that PEFT is a techniques where you keep the core model intact without changing that model weights. We learned in the part 1 that whole model knowledge is encoded, maybe is there in the as part of the model weights, a giant matrices of weights in each layer, right? We are having a lot of those matrices. Now we are not going to change all those matrices. Instead, we will go and see in a couple of slides that we are going to add two new matrices to that existing matrices using a technique called LoRA. So we are going to understand what the LoRA technique is all about and how it works, and we'll see the step-by-step process of LoRA technique. Now let's break down what PEFT really does. but in a slightly technical term. So you can see that on the left we have a giant model. Think of it like a 7 billion parameter model or 70 billion parameter model or any like huge model. If we choose to fine tune it, traditionally we need to update every single parameter. That's what the big red arrow represents, a full fine tuning. So is expensive, slow and memory intensive. So you are retrain the whole engine just improve one part, right? Now the same model, but look into the other aspect. But you take the same model, you see that is in the on the right hand side of this figure you see a small lock. What does it represents is that you are actually locking the model, you freezing all the model weights. So we could use some of the PEFT strategies like LoRA or prefix tuning or adapter. Say let's keep the core model frozen, instead we'll train only small modules. So you see that on this little arrows here on the LoRa prefix tuning, what they're trying to do is they're trying to update, we are just only trying to update say a 0.1% to 3% of the parameters. That's a massive save in the compute and storage. It just like, to give an example, it's like adding a sidecar to motorcycle rather than rebuilding the whole bike. So what is the trade-off here? You lose little flexibility but gain huge benefit. You are going to lower the cost, faster iteration and fewer resources needed. So this is why PEFT is becoming the new standard in fine tuning large language models, especially in, if you are fine tuning a large language models, the PEFT is almost like a default standard to fine tune the model. So next, understand a technique called LoRA, low rank adapters. First understand what is low rank means and what is adapter means, and then we'll go through a step by step process of how the LoRA works. We'll take one simple example, the way we took the model pre-training phase, we take the same example, walk it through step by step. Now let's talk about, before we actually go into the details of LoRA, first talk about what is low rank really means. Not with some math formula, but looking at how information is stored in the matrix. So you can see that on the left, I have a full rank matrix. It is a 3 by 3 grid with random looking numbers. And more importantly, each row is completely unique. That means you can't build one row by scaling, combining others. The matrix contains three independent directions, or what we call rank of 3. So think of these like, three different flight paths. It could be north, east and up. They each take you somewhere new. You can't get one from other. Now look at the right side, the low rank matrices. At first glance, it looks like the first matrix, 3 by 3 matrices, same shape. But look closely, the second row is exactly half of the first row. Third row is like 1.5 times the first row. So even though there are 3 rows, they all point in the same direction. They are just scaled version of one another. The matrix has got only one unique direction. The other are just, we can derive other based on one matrix row. So this is we call a rank 1 matrix. It's a low rank. So a rank is equal to the number of truly independent directions in the matrix. A full rank means more complexity and freedom. A low rank means compressions, fewer direction but still meaningful structure. And this is a simple idea. Fewer independent direction is what makes LoRa so efficient. But we'll come to that next later. But again, another concept is also remember is that you could always decompose, you can always factorize say a 3 by 3 matrix into 3 by 1 matrix and 1 by 3 matrix. I think these are the two essential basics you require before you can actually start understanding LoRa. So what is the rank of a matrices, and then how you can actually factorize a n by n matrix into n by 1 into 1 by n, like 4 by 4 matrix into 4 by 1 and 1 by 4 matrices. Once you understand this, then we'll now understand what is an adapter means. So in the low rank, what is a low rank means, what is an adapter means. Then we'll go and take an example and run through one by one example of the low rank adapter flow. Now let's break down what adapters actually are and how they work inside a transformer models like a GPT or Llama. So when we train a large language model, we are dealing with millions or even billions of weight. That's what we saw in the our last video on pre-training, spread across multiple layers of transformers. If that's what you see when you open Hugging Face Llama model, if you go to the files and version, you could see that there are multiple layers. In each layer there is a big matrices of weights in each layer, right? So these layers are like a brains, the building blocks. So each one transform the input, embedding, or maybe apply self attention, mixes information and pass it on to the next layer, right? You give an input in each transformer blocks. You have an attention mechanism that try to understand how each word has to pay attention to other word, and then you have a feed forward layer which will enrich this particular text with more information and then pass it on to the next layer. Like that you have multiple layers. Maybe it could be 18, 32, like that, large number of layers. In each layer the information what you have get enriched. Now full fine tuning means, as we told in the previous, updating every single weight in every layer. So that's expensive and it can also destabilize a model, especially if you only have a small fine tuning data set. So instead adapters offer smarter alternative. So what are adapters? Adapters are small neural modules inserted in each transformer layer, usually after the feed forward layer. You can think of them like a plug-in upgrade that fine-tune model behavior without changing the original model knowledge. So here is how it works. So each adapter has got two main parts: a down projection layer that compresses the transformer hidden state into smaller vector, reducing dimension, say some 512 to 8, and then an up projection layer that expands it back to the original size, which is 8 into 512. Here is where we apply the need to understand. This way I told in the previous slide that you can factorize a n by n matrix into say n by 1 into 1 by n, right? That's what here up projection and down projection was doing here. So between these projections, we train small set of weights that learn the new task, like whether how to answer a question in a chat-based style, or how to get a domain-specific knowledge on finance, right? And how to get maybe some legal knowledge, right? So the beauty here is that the rest of the model, the massive pre-trained weights, are frozen, so they don't change. Only the small adapter parameters are updated. This makes training much more efficient. It's memory efficient, faster, and modular, meaning you can swap adapter in and out of different tasks. So think like this, right? So the base transformer model is your something like a backpack of a general knowledge. So adapters are specific add-ons like a map of, say for example, you are packing a lot of things in your bag, but you want a specific knowledge, like you want to have a map of one city, or maybe a toolkit for one job you pick, you add to your bag before you go out. These are nothing but adapters. So just to give more simple analogy, so they lets you to specialize model without retraining the entire thing. So this techniques introduce actually in the transfer learning research is now actually the foundation of LoRA, which is the low rank adapters. So we'll explore that next. So we are going to see a step by step process of how LoRA works. But to summarize so far, layers are the core units of the transformer model, processing tokens step by step. Adapters are tiny trainable addition inside each layer, allowing us to fine tune the model very in a low cost manner and effectively. And that's what makes adapter based training so powerful. Now let's begin with the step by step. Now the step number one. So the step number one is, you see that we have a base weight matrix W, which is in this example 10 by 10. Of course in real world it's like very huge, but for this example let's take a simple 10 by 10 matrices. This represents the part of the pre-trained transformer. For example, a projection in the attention or a feed forward layer. Now, so this weights is completely frozen. So what the frozen means that we are not going to touch this matrix. We're not going to change anything in this. So in the middle, we add LoRa adapters, two small matrices A and B. So matrix A is a down projection. Maybe the image might look a bit different, but in real world it could be something like a 2 by 10. And at the beginning, it is all filled with zeros. And matrix B could be a projection matrix which is 10 by 2 matrices initialized with very small random values close to 0. So these adapters are only trainable parts. The idea is simple. You have compressed a 10-dimensional hidden state into two values and we expand those values back into 10, forming a small adjustment. That means if you multiply a 10 by 2 matrices and 2 by 10 matrices, you're going to get 10 by 10 matrices. That's the whole idea. So you are having your because in 10 by 2 matrices you store less number of parameters, right? So but you are able to store less number of parameters means it requires less memory footprint, less processing, less computing power required for that. So, and what is some of the key points is that since A is initialized to zeros, the side path, when we start, there is no change in output. It looks like a pre-trained model only, right? Because we have not started, we just only initialize these two matrices. So effectively, the delta W in this case is going to be 0. So at this stage, the model behaves exactly like the base model. So we have initialized the matrices, but there doesn't have any actual values. So whatever the value you are getting at this point will be same as a base model. Now we'll see what happens, how these two matrices will evolve as we train the model. Again, from here on, we do the same thing, like we do the forward pass, back propagation, the loss, gradient, so everything remains same. So what we do in the step 2 is that we run the forward pass during our instruction data. So again, here we are trying to do an instruction based fine tuning format. So there is a system, there's a user. I'm going to show you how the instruction based fine tuning format looks like when we open the Colab Notebook. But for now, you can assume that you are having instruction based tuning format on the left, where you have a system, user and assistant field. This is converted into tokens and the hidden state that flow through the transformer that we have seen, like what we saw in the last session also. So as the hidden state pass through the transformer layer, they encounter LoRa adapters. Each adapter consists of a small matrices A and B. At this stage, as we see in the previous slide, matrix A is initialized to 0, matrix B is initialized to tiny random values. Because A all 0, the LoRa side path contributes essentially nothing. So again, on the right, you see that the models, the predicted next token. In this example, it might be the word physical. It says explain data between physical and monetary. Something assume that it is predicting next word as a physical. So the important point here is that during the forward pass, as I discussed in the last session also, we are not updating any weights. The LoRa adapters are present but inactive, so the models behave just like the base model. Now it prepares us for the next step, where the back propagation will send error signals into A and B so that they can start learning. So now we are at the step 3, the backward pass. Here what happens after the forward pass, the model makes a prediction and we compare it into correct answer. The difference between the two is called the loss. We discussed again in the last session again. So during back propagation, this loss sends signal called gradient backward to the network, tell which part need adjusting, right? So the key thing here is that since the big pre-trained matrix W is frozen, none of the values are changing. Instead, the gradient flow only into the LoRa adapters, the two small matrices A and B. Here, matrix A is like a filter. At the start, it was all zeros, so it didn't notice anything. Now it begins to adjust so it can pick up patterns from the input that are useful for the task. For example, when the input mentioned physical policy, A start to learn that this is an important signal for the output. And matrix B is like the amplifier. It takes a filtered signal from A and learn how to add it back to the model's prediction. For example, the model output physical, B helps to guide it to follow with monetary instead of something unrelated. So to summarize, the A is no longer zeros, it is starting to capture the task relevant cues. And B is no longer some just random numbers, it is starting to use those cues to improve the prediction. So together A and B form a small adjustment layer on top of the frozen model, and this is a very step where LoRa actually begins to learn. So here I'm just keeping a simple example in numbers of how the the LoRa adapters A and B actually start learning after the backward first. You can see that we are having a small hidden state like 2, 1, minus 1. This vector is coming out of the transformer at this layer. In the middle layer you see matrix A after its first update. It started all zeros, but now it has got a value 0.1, minus 0.2, 0.05. That means A is beginning to decide which part of the hidden state matter more, giving weight to the first element, downplaying the second one, and keeping little influence from the third value. Below the matrix B, it started to learn a tiny random noise, but after the update, its values are 0.05, 0.01, 0.03. B is learning how to take the signals that A picked up and re-expand it back to the model space. So on the right, we multiply A and B to form a small 3 by 3 update matrix, which is delta W. The numbers are very small, but the tiny adjustments are added on top of this frozen pre-trained weight. The key point is that A and B together form delta W. This is the first time LoRa start making a real adjustment to the model. It's small now, but repeated across many examples, these updates add up to the meaningful fine tuning. Now in step 4, we can finally see how LoRa applies its update to the model weights. On the left, you see that large matrix, which is original matrix weight, frozen weight, which represents a pre-trained weights. Notice, that now we are having a learned weights, which is in the delta W, the update matrix that comes from the LoRa adapters A and B. So this is a much smaller in scale, filled with the numbers, but it carries adjustment. So what does this the learned weight update? It contains a knowledge very specific to the finance domain. So that means you are giving all sorts of instructions, knowledge, documents about a finance domain. So this delta W, this is containing only the containing only the weights related to the finance. So now the original model weight W and this delta W, when we combine them, this gives us the effective weight that model actually uses during the training and inference. So we are actually overlaying the delta W on top of W. So that's what you can see that the big idea. You are not now you can see that if you think that W in real world is a billion parameters model, that means it will have this matrix will have a huge, it could be 4096 by 4096, like hundreds of this type of weights. Instead of you doing that, you are actually touching only the small matrices A and B, and you are actually attaching them, merging them with the main W, so that during inference and everything, it is using combined knowledge of both what it has learned in the pre-training and on top of it the fine-tuning phase. This is what we call, when I say initially we are adding a small adjustment, tiny layer, tiny updates to the existing layer. This is what I mean, like you are adding again, end of the day, we should understand that when in LLM everything is nothing but set of matrices. Whole LLM knowledge is nothing but matrices. Every time you ask some questions, it is doing all this matrix multiplication, and then before it, and maybe after that, it is going through all the layers and it is doing all the softmax probabilities. Again after that, it is going to do the sampling, top K, top P, temperature, everything. But end of the day, these weights are what actually matters when you depending upon. That's why when you say a 7 billion parameter model versus a 70 billion parameter model, the 100 billion parameter model might have a more reasoning. As the parameters increases, the model reasoning capability increases, because you are packing all the model knowledge in this model weights. So now we have seen the understand what is the LoRa is how it works. Now let's see the LoRa in action. So in the previous session, we have loaded this model using the Hugging Face. We have seen the response of this model, and it's basically, but you're going to see the magic now, like when you fine tune this model, how the response is going to change drastically. And we are again to as I told, to fine tune, there are multiple frameworks. Like Unsloth is a one framework where you can use it to fine tune the models. It has got APIs, it's kind of faster. And then there is another which is UI based, where without writing any code you can do this, like this Llama Factory, where you can actually just pick up any model. You can actually configure all the parameters, you can point it to a data set, and then you'll be able to fine tune the model. And there is another framework called Lamini, which is also can be used for the fine tuning. But in this case, I'm going to use the Llama model. I'm going to use Llama model, but I'm going to use Unsloth framework to fine tune this particular model. Next, understand the data required for fine tuning. So to do any fine tuning, you require data. Typically, this data is called instruction based fine tuning. Basically, it is in a specific format. So there are a lot of data sets available in Hugging Face. If you want to try something fine tuning, you don't have to generate the data from scratch. You can use some of the already available data sets in Hugging Face. So I have used this data set called finance instruction data set. It is having around 500,000 records. You can see that how they have actually formatted. You can pick up anything. It is having a system, user is asking a question, assistant is giving this answer, right? So this is how the instruction based finding data set look. It is having a lot of record, 5,000 rows are there, and then you can see the model card. You can run some queries, and then you can check the this data set. And then dataset card is also here. You can see the files and versions, some instructions on this data set. Okay, so we are going to use this data set because this pretty decent data set with a lot of information. It can support both conversational, it can support both financial questions and answering, for even for RAG application this supports. So I'm going to use this data set. Just this is how the example looks like. You have a system, you got a user, you got an assistant. This is typically the instruction based fine tuning data set looks like. So we are going to take this particular data set, and then we are going to fine tune our Llama model on this data set. So remember, we have a pre-trained Llama model, and then we are going to fine tune the pre-trained Llama model on this data set. So in the last session, we have seen this pre-trained model, okay, and it has given some response. Now let's see how to fine tune the model. So as we told, we were going to use a framework called Unsloth. So here I'm doing install. Again, this pre-training will take at least, fine tuning will take at least 2, 3, 4 hours. So I have already fine tuned the model. So I'm going to walk you through the code. So here I'm importing all the libraries, but I'll just straight away jump into actual LoRa configuration, which is very important. These are all standard code you can understand, but understanding the LoRa configurations, what configurations will impact how the fine tuning is very important. That's where I'm going to focus more on the LoRa configurations. So let's understand these configurations. So first we'll get this PEFT model. This is a model. The first one is the rank. Okay, so rank is equal to 16 or R is equal to 16. So this is LoRa rank. It controls the size of how LoRa low rank matrices that approximate the weight updates. So a larger R means you will have more trainable parameters, which allows adapter to capture rich update, but it also uses more memory and computations. So common choices like 8, 16, 32, 64. So you can think of this like a resolution of your camera. A higher resolution capture more details but cost more storage. The next one is the target modules. Next one is this one is the target modules. So we are having here Q proj, K projection, B projection, and O projections. So these belongs to the attention mechanism, which is query key values output, which is your QKV matrices in the attention mechanism. Next one is gate projection, up projection and down projection, belong to the feed forward block, responsible for transforming the hidden state after the attentions. So by targeting these, we are fine tuning the model in most efficient manner without touching everything. So you can think of this like, suppose if you're renovating a building, instead of renovating entire building, we only upgrade the rooms where the most action happens. So for example, you have a living room and then kitchen, the bedroom, this is where you live most of the time. So you are going to upgrade only these rooms. You are not going to instead touching entire home. Because of these models are very critical, we are going to touch only these models. Next one is LoRa alpha. Okay, this is the scaling factor applied to the LoRa adapters. So or maybe you can think of another way is like how much of influence your LoRa adapter has to be there on actual the matrix the model's inference, right? That's what the LoRa alpha is saying. So LoRa dropout is equal to 0. This is dropout is a type of a regularization technique so that you can randomly drop some neurons as part of training. So in this case of training, we are making it 0. That means we are not using any dropout. So this is most optimal for LoRa since adapters are already small and we don't need a dropout. A regularization technique like a dropout may not be required at this stage. And we are all setting bias is equal to none. So this specify whether the train bias term in the model. So none means don't touch any biases, which is fastest and which is more memory efficient. So in most cases, bias doesn't provide additional benefit during the LoRa training fine tuning. So none is chosen for efficiency, or you can also use LoRa only, or you can use all, but in this case, none should be good enough for us. Next one is the gradient checkpointing is equal to unsloth. So gradient checkpointing is saving memory by recomputing activations during a backward propagation instead of storing them. So unsloth is an optimized implementation that reduces your VRAM by 30%. That's why we use unsloth, so that you actually reduce the memory. It is much faster. In fact, I have experienced this. I have fine-tuned this model using both traditional, PEFT-based libraries from transformer, and then using unsloth. Unsloth performed almost like half the time faster. The next one is the random state, which is this is a seed of random number, for a random number generations. So the reason is it ensures that reproducibility, so the results can be replicated exactly. And rest everything some LoRa config, both of them are one is for use RS LoRa. This is, I guess, I'm not fully aware of this, but it's kind of a rank stabilized LoRa. This is, you can set it by default false for most of the times. The reason means we are using just a standard LoRa. Okay. And the next one is LOFT config, which is I think it is a kind of an experimental technique for quantization aware training with LoRa. So it allows LoRa adapters integrate with quantized models more smoothly. So none here means we are not enabling this one. Okay. So these are the LoRa configurations. Next, we'll see some after this, we load the data from the Hugging Face. This is same data we have seen previously, right? So we are loading this data. We can see the sample data here. Next, we need to convert this into the format required by unsloth. So every framework you use will have its own data format when you do the fine tuning. So we are converting this data into the format required by the unsloth. Next, after that, we are having this SFT trainer. Let's quickly walk through some of the important configurations in this. Then we will see the training part. Next is that this is a model, nothing but the model we are using Tokenizer is the tokenizer for the model. As we discussed, every model it's have its own tokenizer. The data set we are passing, this is a, what is a field in the data set which is having that text, and then the max sequence length, this is nothing but caps each training example to a maximum token length. Okay, and then next one is a data set num is equal to proc is equal to this is allowing, that means you are processing with two CPU workers in parallel. Now we are having packaging is equal to false. This is nothing but keeps each training sample separate. So if it is set to true, it stitches multiple short samples into one sequence, which speed maybe it might speed up the training up to 5, but it might blur some of the sentence boundaries. Next one is the training arguments. So we are having per device train batch size equal to, what does it means is that only 2 samples fit on each GPU step. Okay. Next is the gradient accumulation which is equal to 4. So what it means is that instead of updating the weights after every 2 samples, it waits for 4 minimum batches, accumulates the gradients, and then does one update step. So the effective batch size, now we can see that you are giving only 2 samples per GPU step, and then you are updating the gradient after every 4 mini batches. So effective batch size is nothing but 8. 2 times 4 is equal to 8. So this is like a teacher giving a grading every 8 homeworks. Okay, assignment instead of every 2. So next one is a warm up step. It is very similar, like you warm up before your any exercise, right? So the learning rate ramps up gradually. This prevents very any unstable weight updates at the beginning. So next one is max step is equal to -1. What it means is that train me on entire data set, not just the some samples. But if you want to do some quick testing to see how the LoRA configurations are working, you can see some 100, do testing for say 10-15 minutes and see everything's working fine. Then you can start a full fine tuning. So these are the FP16 or BF16. These are the flags to check if GPU supports the bfloat 16 precision. If you use BF16, if not, it falls back to FP16. So both will save your RAM versus full precision. Next one is the logging steps, which tells me like how often I have to log all this, my loss, in the logging steps. That means I'm logging every one step. Next one is optimizer. This is the, we are using Adam 8-bit optimizer. Basically 8-bit reduces the memory usage significantly while keeping the performance close to full precision Adam optimizer. Next one is a weight decay, which is applying a small penalty to large weights to prevent the overfitting. So next one is scheduler type, which is linear. Linear means the learning rate start high and linearly decays to 0 over training. So that the model will converge smoothly. So next one is your output directory, save steps and save total steps. Nothing but what is output directory, how many at how many steps you want to keep saving so that you don't lose the model state if something happens in the middle. So once we do this, then the next step is to start training the model. Now it keeps printing you can see that when you start the model, the loss will be higher. As the training progresses, the model loss will be keep on like 1.62. Let's see what is the model like. You can see that the loss is going down as we go across. So it is doing like, I think it has got more than 2000 steps. Okay, so it has got, you can see that the weights are going down. So once everything is done, it saves a model. But since we don't want to lose the model after training, we can save the model into Hugging Face again, so that I can actually get the model back again, read the model again from the Hugging Face. So next what we'll do is we will execute a Gradio UI where we are going to compare the model response pre fine tuning and post fine tuning. So now we can see that I'm actually having this, I'm installing all the libraries. So this is all the required libraries for the GPU available, just printing something. I'm again logging into Hugging Face, installing all this for quantization. We are loading all this model. Now I can see that I'm loading two models. This is my base model. This is my fine-tune model, which I have saved in the previous example, previous fine tuning. So we have seen this model loading in the previous session also. So I'm not going in details of that. For now, we have loaded these models. We want to first see the comparison. So again, I'm having a DeepSeek here for a LLM as judge. So what I'm doing, I'm having a prompt like a response from a base model, response from fine-tune model. I'm asking to compare on accuracy, completeness, financial expertise, and practical value. Now this is our generate response method where we are asking the model to generate the response. So if it is a fine tune, we need to pass in a specific format. If it is not this one, like all these tokens, temperature, everything is configurable, then here I'm actually passing both the questions and then asking the model to compare. And then this is again, I'm having some sample questions. This is again all the Gradio UI again, I have used Claude to generate all the code. Important thing I want to show here is that we are using a stream generated response. That means the model will generate the response as and when it is having the next token. It won't wait for entire response to be completed, right? So it keeps on outputting the response. This is all Gradio UI, all the CSS, UI and everything. So just to format the model and everything. So we have executed all these things. Now we are going to launch this particular code. Okay. So now I'm going to run this. So first we'll execute this one and then we are going to launch the UI. So when you launch the UI, you can wait for some time. Now you can see that it has, of course, I can also open this model in maybe another UI, another browser window. Let me do that. So this is our Gradio UI to compare the model. So now this is a primary model, which is Llama 8 base model. So I am using the Finance Llama 8.3. This is our fine-tuned model. Okay. So I'm going to load the selected models into the memory. Now it will take few minutes to load this model. In the meantime, we can work on, so this is our max number of tokens. Let's make it 500 so we get better response. Keep temperature at 0.7, that's fine. So I'm having some sample questions. Let's pick up some questions here. Maybe let's see what are the benefits of 401k retirement plan is what I'm checking. So now I'll ask this question to the base model and see the response. We'll ask same question to this model, see the same response. We'll pass both the outputs to DeepSeek and then see the DeepSeek analysis. Now let's see get analysis. When you see get analysis, now we can see that since we are doing streaming, it is printing. So the response you're getting is now from the base model. Okay, you can clearly see the benefit difference actually different between the base model, the way it is giving the output versus a fine-tuned model. Now we can see that fine-tuned model is properly categorizing, giving subheadings, everything. In the fine-tuned pretrained model is just dumping the information. Okay, but here it is actually giving properly in a structured format. That's what the difference between the fine-tuning versus a pre-trained model. Now after this, we are going to pass both to DeepSeek and see what response DeepSeek will give. Okay, and what is analysis from the DeepSeek. Now now both has completed their analysis. Now let's see the response from DeepSeek. It will take some time because now after these two steps only we are calling DeepSeek. So let's wait for the DeepSeek to come back, and then we are going to do same thing again once we do the preference based fine tuning in the next session. We are actually going to same thing. We are actually going to compare now this fine-tuned model with a preference based fine-tuned model. So now the DeepSeek has given its response. It is saying that fine-tuned model is more accurate and comprehensive, it correctly lists, and then financial expertise, it says it demonstrates superior. Now you can say that base model has got basic knowledge but lacks a depth by covering complex critical, predictability and actionability. So in some summary, the fine-tuned model response is superior way. Of course, this is, we can also use some metrics and everything, but I'm using just a deep seek to just compare the output from both the models. So this is about, we have seen the difference. Now in the next session, we are going to see the difference from, we are going to learn what is a preference based training.